In this session, I will be discussing on how to determine the Jacobian matrix in a parallel manipulator. So, in the last lecture, we have in the earlier sessions we have seen how to determine the serial manipulator Jacobian matrix. So, how we determine the serial manipulator Jacobian matrix? We had started with the propagation of the linear velocity and the angular velocity vectors, and then we reorganize this angular velocity vectors into something times the joint rate, and then we equated that to a linear velocity and angular velocity of the end effector. So we could uh, start from uh, 0, which is a fixed coordinate system, propagate upwards to the link 1, link 2, and so on, right? So in this session, we will be seeing at the parallel manipulator Jacobian matrix. So in parallel manipulator Jacobian matrix, we do not have a single way of going from the fixed to the chosen end effector. There are multiple parts, multiple loops. So we need to look at how to obtain the parallel manipulator Jacobian matrix. So in a parallel manipulator, you have both actuated and passive joints. So the configuration vector or the configuration space vector Q, this contains both theta and pi. And we have been using theta to denote the actuated joints and pi to the passive joints. So the loop closure equations do not contain all the joint variable. So for example, we have, no, if we have a 3 RPS parallel robot, then we have to break up at the spherical joint. Then it did not contain the joint variables of the spherical joint. So other important thing is that there is no natural choice of the end effector. There is no natural choice of the end effector. So hence we cannot do velocity propagation. So we do not know which one is the end effector and where to start from and where to end. Okay, so in a platform type parallel manipulator like the Stewart manipulator or the RPS, 3 RPS manipulator, the position of the centroid and orientation of the platform is of interest most of the time. So how do we find the linear and the angular velocity of the centroid on the top platform, and also the orientation of the top platform? So given the orientation of the top platform, and if we choose that the centroid is the point of interest, right, so it is the point of interest, the angular velocity of the top platform or the coordinate system can be obtained by that is r by this expression, that is this r dot, this is r dot 0 to tool, and r of the tool frame relative to the zeroth frame transpose, right? So remember, I had we have discussed that in general the space fixed angular velocity vector can be obtained by using this expression, and we can rearrange this expression once we have obtained the space fixed angular velocity vector into a matrix, which we call it as q dot, right? So now note that there will be both theta dot and pi dot, right? Q will contain both theta dot and pi dot because the position vector or the rotation matrix of the top platform or the tool coordinate system will contain both theta and pi. Likewise, the linear velocity of the center of the top platform can be obtained as in this case the sum of the linear velocity of the three connection points. Okay, the sum of the linear velocity of the three connection points. So in the case of 3 RPS, we had three connection points, three that is three spherical joints, and we can obtain the velocity of the centroid as a mean of all these three velocity vectors. Right? So we can obtain the velocity of the centroid as a mean of all these three velocity vectors relative to the frame 0. Right? So for Stewart platform with many other connection points, again we can obtain um, the similar angular velocity and linear velocity vectors. So this matrix, that is this matrix of j omega of q of the tool frame relative to the zeroth frame, which is a function of q, and the matrix jv of q uh, uh, of the tool relative to the zeroth frame. These are the angular velocity and the linear velocity Jacobian matrices. Whereas q dot, it is the time derivative of the configuration variable q. Right? So the linear velocity and the angular velocity vectors are functions of q and q dot. However, in a parallel manipulator, only the actuator joins theta dot, or assume that there are n of them. Let us assume that there are n actuated joins. So the remaining m passive, the m passive joints can be obtained from direct kinematics. We also need the expressions for those uh, psi, size, the rate of change of the passive joint variables. That is also required. So, and obtain the linear and velocity in terms of only theta dot, because theta dot are the ones where there are motors. We know that what is the actuated joint rate. So we should be able to find the linear and angular velocity of the chosen output link in terms of the actuated variables. So basically we need to find this pi dot in terms of theta dot. We have to find the pi dot in terms of theta dot. So how we do that? So we can obtain this from the loop closure constraint equation. So for let us start. So the m passive variables, we have m constraint equations. So which is ni eta I for q1 comma q2 comma etc. up to qn plus m is equal to 0. So this is a general form, but basically there are m constraint equations which are of the form eta of q is equal to 0. So it is a vector equation. So we can differentiate this equation and with respect to time. And so when we differentiate it with respect to time, we will get the theta dot and q dot. We'll get theta dot and q dot. So when you differentiate this equation with respect to time, we'll be getting theta dot and sorry, pi dot. And then we can reorganize all the terms containing theta dot in a matrix, which we just denoted as k of q. And then we will be, the remaining terms in pi dot, the remaining terms in the matrix, that is denoted as k star q. So we can always do this. Why? Because we can take the derivative of these constraint equations. We can only get theta dot and pi dot. We will not get any other nonlinear terms in theta dot and pi dot. So the columns of this m cross n matrix K of Q, right? The columns of the m cross n matrix K of Q, they are basically nothing but the partial derivatives of eta of Q, right, with respect to the actuated joint variables. So just by chain rule, d eta by d theta into theta dot will be this term in matrix form, that is k of q in matrix form. So likewise, this k star of q, it is an m cross, this is an m cross n matrix, right? M cross m matrix, Why? Because there are m constrained equations, and we take the partial derivatives of eta of q with respect to the passive variables phi, which are m of them, then into theta dot, right? So this k of q, it is a m cross n matrix, whereas k star of q is always m cross m matrix. So it's a square matrix. So that is what I'm mentioning again. K star of q is always m cross m square matrix, and k of q and k star of q are functions of both theta and phi. So let's just continue. So if the determinant k star is not equal to 0, then I can solve for pi dot, right? I can solve for pi dot, which is minus k star inverse k theta dot. So you can see that this is a linear equation. If the determinant of k star is not equal to 0, we can take the determinant of k star. Yes, it is a square matrix. So pi dot is equal to minus k star inverse k theta dot, right? So now we can go back to the angular velocity expression, which is omega of the tool frame related to the zeroth frame, and it is partitioned into two parts. One is j omega, one is j omega theta dot, and other one is j omega star pi dot. So we can always do this because the linear and the angular velocity vectors are always linearly related to theta dot and pi dot. Similarly, the angular velocity, or sorry, the linear velocity of the tool or the chosen point on the platform or on the chosen output link can be written in terms of jv theta dot plus jv star pi dot. So once you have this, we can substitute pi dot in these two equations. So if I substitute pi dot in the first equation, I will get the angular velocity of the tool, right? So that is j omega minus j omega star k star inverse k theta dot. So you can see that this pi dot will become minus k, that is this one, that is k star inverse k theta dot. That is your pi dot. So this is your pi dot. And then we can take all this together, and we will have j omega, so minus j omega this, right? So likewise, the linear velocity of the tool will be jv minus jv star k inverse k in times theta dot. So we can now define an equivalent Jacobian matrix for the angular velocity of the parallel robot. So this j omega equivalent and jv equivalent. So jv equivalent is defined by jv minus jv star k star inverse k, and j omega equivalent is defined as j omega minus j omega star k star inverse k. So it is really straightforward. So all I have done is, if the determinant of k star is not equal to 0, I have solved for pi dot and then substituted back into the expressions of the linear velocity and the angular velocity and just reorganized it, right? So now with that J equivalent JV and J omega, that is JV equivalent and J omega equivalent, we can write the equivalent Jacobian in this form. So we have on the left hand side the linear velocity of the tool and the angular velocity of the tool, right? So this linear velocity of the tool and angular velocity of the tool, they are separated by a dash here. So remember this as meters per second, then this is meters per second and this is radians per second. So these are different units, and we can write together this as j equivalent of 2 frame to 0 into theta dot. So what is this that is j equivalent of tool frame to 0? So this is a 6 cross n matrix. This is a 6 cross n matrix, and here we will contain the first 3 cross n rows are from JV, that is JV equivalent, right? JV equivalent, and the next 3 cross n rows are from J omega equivalent. So this is the matrix which is the parallel manipulator Jacobian matrix. So like in serial manipulators, it is not true Jacobian. Okay, so this is not a true Jacobian matrix as in a serial manipulator, in the sense that it is not derived from the derivative of a vector valued function. Okay, it contains, the top half contains units of meter, the bottom half contains unitless. So at a known q, we can solve or we can relate theta dot with the linear and the angular velocity of the tool. So now, if you know what is q, if I know what is q, this j equivalent of the tool to 0 is a function of q of the configuration. So at every configuration, uh, this particular j equivalent will be different. So if I give you theta dot, you can multiply this j equivalent with this j equivalent, and then you can obtain the linear and the angular velocity of the tool. Right. So very similar to serial manipulator Jacobian matrix, except now that we have taken some effort to eliminate the passive joint rates and obtain an equivalent Jacobian in terms of only the actuated joint rates. So like serial robots, the serial manipulators, that is this JVEQ, can also be used to define the GV equivalent for parallel manipulators. So remember, we have in during the geometric interpretation of the Jacobian matrix, we have taken the J transpose J, and then we have found the eigenvalues of the equivalent J transpose J. So in this case, we have to find GV equivalent, which is as given here, that is JV minus JV star K star inverse K transpose into JV minus JV star K star inverse K. So this JV equivalent, it is symmetric and positive definite. Okay, so it is symmetric because it is like A transpose A, right? So it is like A transpose A. So we say it is symmetric, and similar to the serial manipulator, the tip of the linear velocity vector, it lies on the ellipse or ellipsoid, right? So if it is moving in a plane, it lies on the ellipse. If the platform is moving in a 3D space, the linear velocity vector traces an ellipsoid. So however, as you can see, this is much more complicated. It is not simply JV transpose JV. We have all these, that is JV star, K star, inverse, then K. So it also contains the loop closure constraint equations, and the effect of the loop closure constraint equations, because we have taken the derivatives of those and obtained K and K star matrices. So we can also find J omega equivalent. Sorry, we can also find this G omega equivalent again, and using this J omega equivalent, and again the angular velocity can be described as an ellipse. The tip of the angular velocity method is an this is an ellipse or ellipsoid. So if and only if all this is possible, if and only if the determinant K star is not equal to 0. So if the K star were equal to 0, then we could not solve pi dot, because it has this K star inverse, right? So only if the determinant is not 0, this is possible.